In this lesson, we'll cover one of the more commonly deployed difficult style concept areas on word problems in the GMAT Focus Edition, and that's going to be rates and work. So let's begin just by breaking down how rate works from an equation perspective technically. We know that work or distance is equal to rate times time, because how fast you do something times the amount of time that you do it is going to give you your ultimate work or distance. You can also solve for rate by taking your work or distance and dividing by time, or solve for time by taking your work or distance and dividing by rate. So we first need to just understand proportionally how these variables impact each other from an almost theoretical perspective. So you have to confirm first off that rate is listed as a constant, because if it isn't listed as a constant, you can't assume that it is constant. And that can do some strange things in like some unique areas, because if it says Bill takes 4 hours to complete painting a room, unless it says at a constant rate, you don't know that Bill was just sitting down for 3.5 hours and then spent half an hour painting the room. Again, 9 times out of 10, if not 99 times out of 100 on the exam, they'll say it's constant, but you have to beware because they could always exploit the idea that it isn't constant. Now, that said, if we're talking proportionality, we're going to keep one of the three variables constant and then consider the relationship of the other two variables on each other. So if we keep our time constant, when you increase work, you'll increase rate. So this is what is known as a direct relationship. And you can see this, for instance, if we do 20 units in 5 hours, that rate is going to be 4 units per hour, just 20 divided by 5. But if we doubled the amount of work, we're going to double our rate. So if you did 40 units in the same 5 hours, you'd have a rate of 8 units per hour. Now, if you keep the rate constant and you increase your work, you'll also increase the amount of time it takes to complete said work. So if you had 20 units at 5 units per hour, the time is going to be 20 divided by 5, or 4 hours to complete. If you had 40 units, doubling the amount of units, but the same rate, you're going to double the amount of time it will take. So 40 units at 5 units per hour, 40 divided by 5 is 8 hours of time to complete the work. But, and this is where it gets a little bit more complex, if you keep your work constant, so the amount of thing that you need to complete or the distance you need to travel, when your rate increases, your time actually decreases. And this is what is known as an indirect relationship. So we can see this illustrated by if we had 20 units to complete of work. At 5 units per hour, the time is going to be 4 hours. But if you double the units per hour to 10, keeping the work constant at 20, the time halves to 2 hours. So you've got the same proportion. One goes double in the amount of rate, and that halves the amount of time it takes. So you have to notice that if the work remains constant, your rate goes one direction and your time goes the other direction using the same multiplier or factor, ultimately, as we'll see in a moment. So we've got a rate problem example here. We're going to set up the scratchpad as we do for every problem, and we just list A through E, and we probably include the simple numbers in this instance. Then we skip to the end of the problem to identify our sought value, and we label the choices. So we've got how many more hours would it take those remaining workers to complete the order working at the same constant rate? Okay, so we know we're being asked for how many more hours to complete, so we read from the beginning, taking notes and setting up calculations as we go. So 6 workers working at a constant rate at Bill's Widget Emporium are able to fill a certain standing weekly order for a number of widgets in 20 hours. So we know that work is equal to the rate, which you can also articulate as the number of workers times time. We know that we've got 6 workers times our 20 hours, which is 120 units of work ultimately. And our new time is going to be that same constant amount of work divided by the new rate, which is the new number of workers. And of course, if we move on, we find that one of the workers calls out sick for a week and only 5 workers were available to complete the weekly order. So now our new rate or new number of workers is 5. We then find our new time by taking our still constant amount of work of 120 and dividing that by 5. So we find that our new time, our new number of hours, is going to be 24. And of course, 24 minus 20 is our 4 more hours, and our correct answer is A. And if you see the technical solution to this and are comfortable with the algebra that it is ultimately using, feel free to do the technical approach as your first option, because we know that the technical approach is probably fastest if you know how to do it. But if you don't know how to use the technical approach, you can also use what is known as a ratio table. So we've got a sample ratio table here, and you can see it's structured where we've got 3 columns. We've got one for apples, one for bananas, and total fruit as the final. And then we've got 3 rows, the ratio line, our constant multiplier, and our real values ultimately at the bottom. So how do we use this table? Well, the ratio values and the real values will sum to our total parts. So if we know that we've got 5 apples for every 2 bananas, we know there's 7 total fruit in our basket. Similarly, if we know that there are actually 25 real apples in our fruit basket, and we've got that ratio of 5 to 2, there's going to be 10 bananas, and we're going to have 35 total fruits in the basket. And our multiplier is going to be a constant for all of the columns in the proportion. And you can divide any real value by the ratio to find the constant multiplier for the table. So if we took the 25 and divided by 5, we discover our constant multiplier is 5. And you can see if you multiply down any of the columns, you'll get the real values as the product of the ratio and the multiplier. So as it says there. So let's consider our prior problem using the ratio table structure. So you could read from the beginning, taking notes and setting up a partial ratio table as you go instead. So this time we've got workers and we've got hours, we've got ratio as the top line, we've got constant multiplier unknown in the middle, and our new total of workers as 5. And you'll note, we recall from our proportional discussion at the beginning of this lesson that when we lower the rate, we're going to increase the hours. So when the workers go down, the hours are going to go up. As always, you want to logically estimate to eliminate impossible choices. Clearly, we're not going to take 24 more hours just because we lost one worker. So get rid of E immediately. Then we can divide the new total by the original value of 6. So 5 divided by 6 to find our constant multiplier as a fraction, because 6 times 5/6 is 5. And you're going to want to consider this as fractions more so than decimals, just because it's easy to do 6 divided by 6 times 5 is 5. And it allows for a relatively easy reciprocal to be applied. So we use reciprocals to account for the indirect relationship because we know the opposite operation is multiplication. And to divide by a fraction, you're just multiplying by the reciprocal. So we apply that reciprocal to indicate the indirect relationship for the hours as it pertains to the workers. So instead of multiplying by 5/6 for the hours, we're going to multiply by 6/5. And if you did 20 divided by 5, you get 4, and 4 times 6 is, of course, 24. And once again, 24 minus 20 is 4 more hours. But note, we eliminated the trap of choice E if we solve for the wrong thing by just being diligent at the outset and saying, well, we know it's not going to be more than double the amount of time. So then we get to what is probably the most flexible of all of our rate and work structures, which is the rate circle. And you might recall this kind of visual setup from an average circle. And a rate is nothing but an average amount of work done over a period of time. So you've got your worker distance up top, you're going to have your time on the bottom left, and your rate on the bottom right. So this is just a visual representation of worker distance is equal to rate times time. Because if you multiply time times rate, you get worker distance using the circle. And of course, any two values in the circle can solve for the third. And you could use multiple circles to coordinate complex rates as well. And it is possible to add or subtract raw work, distances, times, and possibly even rates if you're combining two different workers. For instance, if one worker does 6 units per hour and the other worker does 4 units per hour, well, we know that combined they'll do 10 units per hour. So you can add these values across multiple circles to work through the construct of a problem that's in front of you in the quantitative reasoning section. So we go back to the exact same structure. So we've already set up the scratch pad. We already know what we're being asked for, how many more hours to complete, and we start taking notes. So we know that there are 6 workers. We know that there's 20 hours. And we've got our new number of workers going to be 5. So we're trying to solve for our new hours. And you want to note our possible alternative tactic clues, starting with the word certain. And we've got an unknown value, a number of widgets dictating the whole problem. So that indicates that there's a possible modeling approach to this problem as well. So once we've identified that there's a modeling opportunity with a rate problem, that basically means we're going to set up a rate circle using an easy total value for the unknown number of the widgets in a certain order of weekly widgets. So you can consider the product of the given values as an easy total. So we know that we've got 6 workers, we've got 20 hours. So we can just say there's 120 units, the product of 6 and 20 as our total work to complete. And this results in a given rate of 1 unit per worker per hour. Because if you've got 6 workers doing 20 hours worth of work, you get 120 units. That means that they each did 1 per hour with the 6 workers and 20 hours. Then you just set up your rate circle, trying to solve for the new rate of 5 units per hour. Because if we take away 1 worker, we're taking away 1 unit per hour. So then we've got 120 units up top. We've got 5 units per hour as our rate in the bottom right. We will divide to find the time using the rate circle, and we see 120 divided by 5 is 24 once again. And of course, 24 minus 20 remains 4. So you've got 3 different ways that you can work through this problem, and that's the flexibility. Now, that said, if you have explicitly combined time, you can bypass the rate circle, you can bypass the ratio table, you can bypass some of the more complex, kind of more logical approaches for this literal formula. Now, our combined time formula of time for A times time for B over time for A plus time for B is just a simplification of the combined rates formula. So you may have seen combined rates somewhere in other resources. We're generally not going to do the combined rates formula because it involves reciprocals and processing them. It's just not intuitive. But if you can memorize this particular application of it for combined time, it can be reasonably applied under the constructs of the exam, and that, under 3 minutes for any question kind of time management. Now, you do have to be careful and confirm consistency of the metrics that you are using. So if it's in minutes, stay in minutes. If it's in hours, stay in hours. If you've got some in minutes and some in hours, think critically about what is the sought metric and work through that. For this formula, only use it for combined time. Don't use it for combined rates. Don't use it for combined work. It has to be combined time, because if you apply it for other things, it's not going to be nearly as direct and efficient. And that's why we generally want to leave it just for combined time. So let's head on over to the whiteboard, and we'll actually take a look at how we can use all of these different approaches to work through a couple of work rate problems together so that you're ready for your own practice on the GMAT focus. So we set up our scratch word, as always, A, B, C, D, E. And I've got real numbers. They're fractions, but they're pretty short. So I'm going to write those out. We've got 1/2, 1, 1.5, 2, and 2.5. Now, you won't want to do your processing of the math using mixed numbers ever, but you can convert potentially what are known as improper fractions, where the numerator is bigger than the denominator, into these mixed numbers pretty quickly if need be, and that'll be our last step. But for now, we're going to skip to the end, and we can pick up after this comma, and we see in how many hours can a single standard photo order at Jabba the Photo Hut be completed if the 2 women work together at their respective constant rates. So we're looking for the number of hours combo, basically. So we know that from the beginning, Jenna and Bella are each available to print a standard order of photos at Jabba the Photo Hut. If Jenna can print a standard photo order in 6 hours, so J time is equal to 6 hours. And Bella can print the same standard photo order in 3 hours, so the B time is equal to 3 hours. How many hours can a single standard photo order be completed if they work together? So now there are a litany of possible approaches. The first we'll do is the technical approach, just because we just saw it, and we know that our combined time formula was equal to the time for A times the time for B all over the time for A plus the time for B. So if you remember this formula, you can go straight to that. And so we've got our combo hours is going to be equal to 6 times 3 all over 6 plus 3. And that's going to be equal to 18 over 9, which is equal to 2. And there is one possible path to solving. Now, if you forget your combined time, we know that we always want to think logically. So let's consider a logical evaluation alternative. And here we can logically say that if we had two J's working together, that would have to be exactly half of the amount of time it took one J. So that'd be 3 hours. And we know that two B's time would be exactly half as well. That'd be 1.5 hours. So we know that the combo has to be in between these two values. So it has to be greater than 1 and 1/2, but less than 3. And that allows us to eliminate choice A, B, and C immediately. And then I'm just down to D and E. Now, that said, we could also, to work through the last little bit here, just set up a little ratio or a rate circle here. So if we just said a standard photo order, so we'll say standard order, and we want to set that equal to a value that is divisible by both 6 and 3, and it's not accidental that it's the same 18 that we could use. So if we did 18, and we'll just have a J structure first, we know J takes 6 hours. So that's going to be 3p per hour. And then if we set up another rate circle here, and we did one for B, it's the same 18 photos. This time it's 3 hours, and that's going to be 2 photos per hour. And then when we combine them, set up the same structure, and I apologize for my wonkiness of the little circles. Drawing freehand has never been a strong suit. But we know it's still going to be the same 18 photos in a standard photo order. We know that, oh, and that's supposed to be 6 photos per hour, not 2, because you do 18 divided by 3, of course, gives us 6. And then if we did 3 plus 6 would be 9 photos per hour. 18 divided by 9 gives us our 2 hours. And there, once again, is our answer using a little bit of logical estimation, evaluation, and the rate circles. So you can see with these rate problems, allow yourself to think about what is the most efficient path to solving in the moment for you rather than just going with the first technical approach that you see. Although in this case, I would advocate for the combined time formula being most efficient if you can recognize it and execute it. So let's scroll on down and take a look at one more example here. Went a little too far there. So setting up the scratch work, we got A, B, C, D, E, put a little line over top. And we're being asked for how many minutes will it take Pierre to pass Renard. So the minutes for P pass R. And I'll know what that means for the next couple of minutes that matters. And I've got real numbers here. So I'll put 2, 30, 60, 90, and 120. So we know that from the beginning, R passes a certain convenience store driving west at 80 miles per hour. So R rate is equal to 80 km per hour. And then we find that 30 minutes later, so after 30 minutes, he passes at a rate equal to 100 kilometers per hour, driving the same direction, traveling west, and on the same road. Provided both drivers continue driving the same direction at their respective constant rates for at least the next 3 hours, how many minutes will it take P to pass R? So another concept that can come up is the idea of directional rates. So when you have opposing directions, then you just take the sum of the rates. So, for instance, if Renard and Pierre were driving in opposite directions, they would be 180 miles further away from each other after an hour because 80 kilometers rather going one direction and then 100 kilometers going the other direction would be 180 kilometers when they're going opposite directions. But if they're going in the same direction, in that case, you need to find the difference of the rates, because that's going to be the change over whatever the time period is. So we know that we've got to consider how much distance has to be made up by Pierre, and we know that Pierre is ultimately going to be gaining 20 kilometers per hour on Renard as long as they keep driving at those same rates, because 100 is 20 kilometers greater per hour than 80. So let's just set up a couple of rate circles. So we know that there's basically the lead for Renard. So we're going to have the R lead. And we know that Renard goes 80 at kilometers per hour, so K per hour. And he does that for 30 minutes before Pierre passes that same convenience store. Now, I don't want to do minutes at this point. I'm going to keep it as just half an hour, because that's going to be the easiest way to just process the rate of kilometers per hour with an hour. So we know that 80 kilometers per hour driven for half an hour is going to give us a 40 kilometer lead for Renard. So now we've got to consider the P catch up. So Pierre has to make up those 40 kilometers, and he does so at a rate of 20 kilometers per hour. So that means we just take the 40 kilometers and divide by the 20 kilometers per hour, and we find that it's going to take 2 hours for Pierre to catch up. Now, of course, we're looking for minutes, so we've got to make sure we avoid the trap up here of 2. But when we convert 2 hours times 60 is going to be 120 minutes, we determine that our correct answer should be choice E. So you've seen a whole bunch of ways to work through rate problems in this lesson. When you're doing your practice for rate word problems, consider as many possible approaches as you can, so that when you encounter these problems on your official GMAT Focus Edition, you'll have a whole list of options for your path forward to give you an opportunity to be as efficient and effective as possible come test day.